Alright, welcome to Unit 8 on Organic Chemistry. And this unit is going to focus on some basic ideas of organic chemistry and the nomenclature, in other words, how to name organic molecules. Our lecture 1 is just referred to as organic molecules because we're just going to look at some of the very basics. Essential questions that need to be addressed is: what is an organic molecule, what is a structural isomer, and what is a functional group? Alright, so let's start off with first discussing what is an organic molecule exactly. Organic molecules are defined as compounds or molecules that contain carbon atoms in them. So these are all covalent compounds, and it is a very large area in chemistry, and there is an absolutely very large number of organic molecules out there. There are so many organic molecules that we cannot count them all. In fact, we are constantly finding new organic molecules in nature, as well as making them synthetically as well. So organic chemistry is a very big field, and it is a very important field in our society and our world. Most of the major molecules that your body is made up of and how your body functions is based on organic molecules or organic chemistry. Important field to study. Alright, so let's get started. The first thing we need to address is: what is a homologous series? What I want you to think of is a homologous series is more of a family of organic compounds. So we divide organic molecules into homologous families, and there are some specific ideas in which, or classification in which, a molecule must fit in order to be in a particular homologous series or family. Alright, and so we're going to address what those qualifications are. So I got some diagrams here of 3 structures of organic molecules. Notice that they all contain carbon in them, and they're all covalently bonded to each other. We have methane, ethane, and propane, and these are 3 molecules from a particular family called the alkanes. And you'll begin to learn more about the alkanes here later on in this lecture. But the alkanes all belong to a homologous series, and these 3 alkanes we're going to use as an example to look at the classifications or requirements in order for a molecule to be in a particular family. Right? So first of all, successive members of a homologous series differs by a CH, that should be actually a CH2 group. We can put a 2, subscript 2 group there, fill that in. So if you look at our methane, ethane, and propane, they differ by adding a CH2 group to molecule. So notice that we start out with 1 carbon, and then we go to 2 carbons, we add another one, and then we add another one. So we just keep on adding a CH2 group to our homologous series, and that's pretty typical. What else is similar about homologous family is the homologous series can be represented by a general formula. So we'll look at those general formulas as we talk about particular organic families. Members of a homologous series show a graduation in physical properties. That's really important. So for instance, if you look at methane, ethane, and propane, their physical properties are going to slightly change based on the number of carbon hydrogen groups that we have. So methane, for instance, has a boiling point of negative 164 degrees C. Ethane has a boiling point of 89 degrees C, and propane is negative 42 degrees C. So what we see is a general graduation in change of physical properties here within this homologulus series. Methane having the lowest boiling point, meaning it's going to boil at a much lower temperature than ethane, and then propane has the highest boiling point. Of course, all of these are, generally speaking, are very low boiling points overall. All right. So again, we see a graduation in properties. The last thing I want to look at, which should make pretty much common sense, is that if compounds are grouped into families, they're going to have or show similar chemical properties. All right, and so that's probably one of the big things, is that we throw these organic compounds into families because of their similarities and how they chemically react. All right, so that's kind of an idea of what a homologulous series is. Make sure you know these 4 points very well. I will quiz you on these 4 points. All right, so we've kind of actually gone over the main features of a homologulous series, and so I'm not going to go back and look at those, but I gave you those list of four ideas, and again, just make sure you know those 4 ideas. All right, how do we represent organic molecules? Well, there are several ways in which we do that. Some you already are familiar with, based of what we've discussed in earlier chapters. We can represent an organic molecule by its molecular formula, but the molecular formula has some limitations because it only tells us the atoms that are involved in the compound and the ratios, and that is it. And that's important, but it doesn't tell us how those atoms are connected together. In other words, we don't have necessarily a Lewis type of structure. And so one of the most important type of structures we can have for organic chemistry are what are known as structural formulas. And we have 2 examples of some structural formulas, one for ethanol and dimethyl ether. Both of these have the same molecular formula, but they are arranged differently. So these are also known as structural isomers, which we will talk about in just a minute. But notice how the structural formula allows us to not only see what atoms are involved in the organic molecule and the ratios, but it also tells us how they're connected, how all of these atoms are arranged in a structure, kind of much like a Lewis dot structure. And so in this class and on the tests and quizzes that we take, whether it's an IB or an AP test, you will be required to write majority of your organic molecules as structural formulas. Another way to reduce the amount of space that these structural formulas take up is to write a condensed structure. And what we do with a condensed structural formula is we just get rid of the dashed lines that shows the connectivity. But as you can see, we can still see how molecule or atoms are connected. So for instance, if you look at this ethanol here and its condensed structural formula, you'll see that the carbon here is attached to these 3 hydrogens. So those 3 hydrogens, the way they're arranged, so you usually go carbon, and then you show anything that's attached to that carbon next. And so we know that 3 hydrogens are attached to the carbon, so we'd show that next, followed by the next carbon that is also attached to it. And notice that the next carbon here is only attached to 2 hydrogens, which is indicated in our formula, and the last is this OH group, which is attached to that carbon. So we kind of show, again, the idea is we put a carbon, and then we show which other atoms are connected to that carbon, such as CH3, followed by any other ones, such as the next carbon, which is then is attached to two hydrogens and an OH group. Okay, if there was another carbon, say a third carbon in this, then we'd put another carbon. If it was attached to some hydrogens, then we'd put some hydrogens and so forth. Okay, so that's kind of how a condensed structure works, and they can be kind of useful to again give us some space, and so that's the compound isn't so large. The last type of structure we'll talk about is skeletal structures. They're really useful. Basically what they indicate is you get rid of all the carbon atoms and all the hydrogen atoms. Instead you use lines. And wherever 2 lines connect at a point, that is where a carbon atom exists. And so skeletal structures are nice because they're really fast and quick. They take some practice to learn how to do. But the problem is that skeletal structures are not a valid structure for the IB or AP test. So in theory you can practice with them and do some homework with them, but do not use them for exams at all, because IB will dock you points, AP will dock you points, and will not recognize it. Alright, so I will kind of go over skeletal structures a little bit more in class, but let's just, for the most part, assume that you're either going to use a structural formula or a condensed structural formula in order to represent an organic molecule. Alright, now what we're going to do is we're going to address structural isomers. Structural isomers are really important to understand. So let's talk about a definition of structural isomers. Basically, they are molecules that have the same molecular formula but different arrangement of atoms. So they have the same number of carbons, the same number of hydrogens, the same number of oxygens or whatever. However, we take those atoms and we arrange them differently to form different structures. Alright? And so here are 2 examples of structural isomers. Notice that they have this, both of them have the molecular formula of C4H10. So we have a 4:10 ratio between carbon and hydrogens, but we're going to arrange those to create these different structures. And out of those 2, we could create what is known as butane and 2-methylpropane. And just look at the differences in how they're structured. This right here, where it looks like a cross down here, really has a carbon right there. Let me write that a little bit better. This really is a carbon. So basically what we're going to do is we're going to take this carbon right here and we're going to change it to the middle one, and then we're just going to connect it, and then creating that new structure. Alright, so one thing you're going to be required to do is to take a molecular formula such as the C4H10 and draw all the possible structural isomers from that molecular formula. It can be kind of a challenge, but we'll spend some time in class learning practicing how to do that and so forth, making these structural isomers. For now, what I want you to know is two important things. One is the definition of a structural isomer, what it means, and two, understand that different structures of the same molecular formula is going to give us different physical properties. Alright? So as you can see, for butane, we have a boiling point of negative 0.5 degrees C, and for 2-methylpropane, we have a boiling point of a negative 11.7 degrees C. So, one more time, structural isomers, same molecular formula, different arrangement of the atoms creating different structures. Therefore, different structures result in different different physical properties. So again, that's important that you need to know that for the quiz, for the class, and so forth. And again, as I mentioned, we will practice this in class, writing structural isomers. Alright, the last thing I want to look at with this lecture are functional groups. This is going to be one of your primary things you're going to have to do before you come to class, is learn the functional groups of organic molecules. Now, these functional groups are going to help us put molecules into particular families. So, as you'll see along this first column here, this gives us the homologous series, which is represented by a particular functional group. Alright? The functional group can be seen here in this column, which we'll look at. The name, or which we should say the ending of the name of an organic molecule based on its functional group has a particular name that allows us to know what that functional group is. And then I have examples there for us. So let me tell you what you need to know to come to class. First of all, you need to be able to recognize the functional group. So, for instance here, let's look at an alkene. All alkenes have double bonds in their carbon atoms, and all alkenes end in ene, and so that's what you would need to know. So what an alkene is and what it ends in. Alright? An alcohol is going to end in an OH group, and it has an OH group and ends in an enol. An amine is an NH2 group and ends in anamine. Alright? And so forth. So let me give you kind of specific ideas. By the way, the R, when you look at the R's here, these R's, all those R's represent usually is a carbon atom. So there's going to be some kind of carbon atom or carbon chain added to that section. That's all. Alright? So let's take a look at some things here. If you had an alcohol, for instance, you would see something like CCCOH. Okay, now that OH represents an alcohol functional group, and you would have to recognize that when you look at a molecule. This is an alcohol. And so the ending to this molecule is going to end in enol. Alright? Enol. And so, for instance, this particular compound is going to be called propanol. Oops. Propanol. Alright? Propanol. And so it ends in an ANOL due to the fact of its functional group. Let's look at some other functional groups here. Let's look at a ketone. Alright, look at your table, look at a ketone. A ketone should have an R and a C with a double bonded oxygen. Oops, let me erase that and bring that down a little bit. Should have an R, carbon with a double bonded oxygen flanked by another carbon. So usually these are carbons. They're flanking this functional group called a ketone. And so you have carbon, 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 double bonded oxygen with a carbon, and these would all be saturated with hydrogens around it. And so you recognize this is a ketone, and that ketone is going to fit in a special homologous group called the ketones. Alright? So most of the functional groups indicate to us what family that molecule belongs to. Alright? So they're very, very important. So what I want you to do is look at your functional group list, and when you come to class, make sure you know each of the functional groups and what their endings are. Recognize them. Let's go back to those again, take a look at those functional groups. So the ones that are really important you can focus on are like the alkanes, the alkenes, the alcohols, the amines, aldehydes, ketones, carboxylic acids. Those will be really important for the SL students, and the AP students. For the HL students, you'll need to also know the rest of these, like an amide, ester, and nitrile. Alright, so HL, you need to know all of these. SL and AP, you only need to know really these groups here, and you'll be good. So SL/AP, and then HL has to know them all. So again, recognize the functional group, what it is, and what the ending, the suffix name for each one of these functional groups. Alright, well, that is it for this lecture. Make sure you go back and review your notes, prepare for the quiz, and specifically what is so important is to know these functional groups and their suffix name. But that is it for now.